Hello everyone. Today we shall discuss the case of homogeneous equations where the characteristic equation has repeated roots, a double root. So let's say we have a homogeneous equation and we write immediately the characteristic equation. And solve it by the quadratic formula. Now, we consider the case where the quantity p squared minus 4q inside the radical is 0. In this case, we have a repeated root r equals minus p over 2. And then we do this. It's a very special situation. Sorry, here I wrote two negative signs. So then we define x1t to be exponential rt, which is exponential negative p over 2t. And this is a solution to our homogeneous equation star. However, we need a second solution. We need two independent solutions to write the general solution. So we define x2 of t, which will be t times x1, multiply x1 by the variable t. So this will be t exponential minus p over 2t. And this is also a solution for differential equation. And obviously, the two functions x1 and x2 are independent. The ratio is t, it's not a constant. Why is this a solution? So I want to prove you this. I shall put x2 in the equation and you'll see that this is a solution. So I want to form x1, x2 prime, x2 second, and put in the equation. x2 prime using product rule will be exponential minus p over 2t. And here keep t, differentiate exponential, minus p over 2 will come in front. T stays, exponential minus p over 2t. This is the first derivative. Here comes the second derivative, minus p over 2 t, minus p over 2, exponential minus p over 2t. This is differentiate the first term, then minus p over 2, again exponential p over 2t. Differentiating t, we get 1. And then differentiating the exponential here, negative p over 2 will come and make it plus p squared over 4 t exponential minus p over 2t. Now we have to put this in a differential equation. Here in the second derivative we can simplify, we can put together these terms. This will be just minus p exponential minus p over 2t. So this is the second derivative. x2 second plus p x2 prime plus q x2 equals. Now we're collecting all these things. Minus p exponential minus p over 2t plus p squared over 4 exponential have to put here t first, t exponential minus p over 2t. This is the second derivative. Then plus p, the first derivative, plus p exponential minus p over 2t minus p squared over 2t exponential minus p over 2t, and then plus q x2, so plus q t exponential minus p over 2t. Now what can we do here? All the terms with t I shall bring together, this term and this term and this term, and what is left cancels out. See, these two cancel out. So I shall factor from the underlined three terms, I shall factor t exponential minus p over 2t. And what is left inside, we have p squared over 4 minus p squared over 2 plus q. Now we do common denominator, which obviously will be 4. The expression here, common denominator. So there will be t exponential minus p over 2t, p squared over 4 minus 2p squared over 4 multiplied top and bottom by 2, and here multiplied top and bottom by 4. Adding all this inside the parentheses, we get p squared minus 2p squared will be minus p squared just one time plus 4q, and all this over 4, and this is 0 because p squared minus 4q is 0. You can write this like with negative in front. Anyway, it's clear. 4q minus p squared is 0. So really, all this is 0, and x2 is the solution for our differential equation. So that's how we construct two independent solutions for the equation, and general solution will be written this way: xt, let me write general form, parameter x1 plus parameter x2, and in our case, in the case of repeat roots, this will be a exponential minus p over 2t plus b t exponential minus p over 2t. So here we have x1 and this was x2, and that's what is the general solution. We can factor the common exponential and write the general solution this way. And of course, if we have initial conditions, we can compute a and b. Let me show you one example. Solve the equation x second plus 6x prime plus 9x equals 0. And here initial conditions. x0 is 3, x prime 0 is negative 4. So this is our homogeneous equation. We're writing the characteristic equation. R squared plus 6r plus 9 equals 0. Immediately reaching for the quadratic formula, r equals negative 6 plus minus root 36 here minus 4 times 9, which is again 36, divide by 2. The result is negative 3. Repeated root, just one, repeated. So we define x1t to be exponential negative 3t, and we define x2t to be t times this. These are two independent solutions for our equation, and we can write general solution xt equals arbitrary constant with the first one plus arbitrary constant with the second one. And then we can factor the exponential, of course, if we want. General solution. Remember, we have initial conditions. When t equals 0, x0 is 3. So we put in this general solution t equals 0, and x0 will be 3 on the left side. When t is 0, exponential is 1, and this is just a, because of t, second term will be 0. So we found a. Excellent. Now we have to differentiate and use the second initial condition. X prime t will be differentiating exponential, negative 3 will come down. This becomes negative 3a exponential negative 3t plus by product rule b exponential negative 3t, and then minus 3 bt exponential negative 3t. Put t equals 0 again. X prime 0 will be negative 3 on the left. Sorry, negative 4. Let's correct that. Negative 4 on the left. On the right side, what we get? Negative 3a plus b plus 0, because the last term will be 0. And then a is 3, so this will be negative 9 plus b. b will be negative 4 plus 9 will be 5. Excellent. We found b, we have a, so I'm writing the solution that corresponds to the initial conditions. 3 times exponential negative 3t plus 5t exponential negative 3t. We can factor the exponential and write it this way. Here, 3 plus 5t. Okay. This is enough for the case with repeated roots. In the case of complex roots, next time we shall do this separately. Goodbye.